All right, so e to the square root of x. I'm just going to say, check out this trick, and we'll see that it works. And after we've seen this one, maybe we would think to use that trick the next time we see something similar. But this is one of those cases where there's a square root involved, and doing like a standard u substitution actually makes things a lot simpler. In this case, it results in an integral that you have to do by parts. So I prefer to have my u's and v's for the integration by parts formula. So I'm not going to call it a u substitution here. I think I'll call it a t substitution. So I'm going to go let t equals square root of x. Again, I'm not doing integration by parts yet. I'm just doing a standard substitution. So the benefit to this, the whole idea behind it, is that it would simplify this to e to the t, which is a lot nicer. So then I would have to write down the differential of this. So this is x to the 1/2. So I end up with 1/2 x to the negative 1/2, or 1 over 2 root x dx. And then I'm going to explicitly transform this differential. So this, the e part is taken care of. That's just e to the t. But what's dx? It's 2 root x times dt. All right, but so again, the goal is to transform everything in terms of t. So I ask, what's square root of x in terms of t? Well, that's just t. All right, so my integral, sometimes I like to just give the integral a name, so it's going to be I, so I don't have to copy it every time when I'm trying to be complete in my notation. So I has been transformed to e to the t times 2t dt. So I'll call it 2t e to the t dt. There's one more thing I want to do. I don't want to have to go back and put everything in terms of x at the end of this problem. And so I'm just going to transform the limits of integration as well. So when x is equal to 0, I've got to figure out what t is, and that will be my lower limit on the t integral. Well, when x is equal to 0, t is 0, because square root of 0 is 0, and when x is equal to 1, so I plug in a 1 there, t is equal to 1. So that was a happy coincidence. We didn't have to change the limits of integration at all. Okay, now I'm looking at a classic integration by parts type of integral. I have a piece that clearly gets simpler if I differentiate it. So if I let u equal t, or if I let u equal 2t, depending on how you do it, I guess I'll just do it that way, then the derivative is just going to be 2, and it's simpler. At the same time, I need the leftover piece to have a guessable antiderivative, and the antiderivative of e to the t is easy. It's just e to the t. So here goes our integration by parts. Let u equal 2t, then du is 2 dt. And then the other piece is dv. Let dv equal e to the t dt. Then v is the antiderivative, e to the t. And then I'm going to apply the integration by parts formula, and I have u times v, so that's 2t e to the t, evaluated as t goes from 0 to 1, minus the integral of v du, so that's going to be e to the t, and the du is 2 dt. I'm going to move the 2 out in front, and the limits of integration again are 0 to 1 on that. So then I'm just going to evaluate the uv piece as I go, and I'm looking for things that simplify. So when I put in the lower limit, that's 0, because multiplying by 0 here makes anything 0. So I don't have to worry about that. Plug in the upper limit, and I get 2 times 1 times e to the 1. So this is 2e. Then I have to do this leftover integral, and the integral of e to the t is just e to the t, evaluated from 0 to 1. And when I plug in the upper limit on that, I get a negative 2e to the 1, and then I have to subtract what I get when I plug in the lower limit. So that double negative will give me a plus 2e to the 0, but e to the 0 is just 1. So those pieces cancel, and I end up with a nice answer of just 2 on this for the area.